Now we're in section 4.5 where we're going to take the things that we learned about in section 4.3 and 4.4 and apply them to graphing functions. So to graph y equal to f of x, we can find all of the interesting and important behavior by doing the following things. First, find the domain. Figure out where the function is defined. Second, find the intercepts. The x-intercept is when y is equal to 0. The y-intercept is when x is equal to 0. 3. The asymptotes. Find the horizontal asymptotes by looking at the limits at negative infinity and positive infinity. And find the vertical asymptotes by, well, there are a variety of ways of doing that, but one way is to check what the limit of the function is at any of the endpoints of intervals of the domain. Then, number 4, we'll find where the function is increasing and decreasing by looking at the first derivative and figuring out where that's increasing and decreasing. 5, we will find the local maximums and minimums, and that oftentimes using the first derivative test is more or less the same thing as finding where the function is increasing and decreasing. Then 6, figure out where the function is concave up and concave down using the second derivative, and find any inflection points. Once you have all this information and you've plotted it all, then you can put it all together and get a really good looking picture of the graph you're looking at. Okay, so let's try using all these steps to graph e to the x over x squared. First, what is the domain? Well, e to the x over x squared is perfectly well defined because it's a ratio of two continuous functions except for when the bottom is 0. So when x squared is 0, or which is when x is equal to 0. So the domain goes from negative infinity to 0 and from 0 to infinity excluding 0. Next, what are the intercepts? The y-intercept is when x is equal to 0. F of 0, well, we just said that's undefined, so there is no y-intercept. X-intercepts, that happens when f of x is equal to 0. When is e to the x over x squared equal to 0? Well, multiply both sides by x squared, and you get e to the x is 0. Well, that has no solutions. So there are no intercepts to worry about here. Next, let's find the asymptotes. So to get the horizontal asymptotes, I look at the limits at plus and minus infinity. At infinity, I've got e to the x over x squared. This is a fairly straightforward application of L'Hopital's rule. It's infinity over infinity. I take the derivative, I get e to the x over 2x. That's still infinity over infinity, so I take the derivatives again, get e to the x over 2. The top is going to infinity, the bottom is a constant, done. So that goes to infinity. So there's no horizontal asymptote there, but this information is important to us. It tells us that as x goes to positive infinity, then y is going to be going that way too. As x goes to negative infinity, e to the x goes to 0. X squared goes to infinity, so 0 over infinity is 0. That gives us a horizontal asymptote at y equal to 0. Vertical asymptotes. The only place that anything can go wrong with our function is at 0. So we look at the limit as x goes to 0. Well, e to the x approaches 1 as x goes to 0, and x squared approaches 0 and is positive. So a constant over something going to 0 will go to plus or minus infinity, and since the denominator is positive, it goes to positive infinity. That tells us that we have a vertical asymptote at x equal to 0. Next, we'll look for the intervals on which the function is increasing and decreasing. So I take the derivative. I'm going to rewrite this as e to the x times x to the minus 2. I'll take the derivative using the product rule. I get e to the x times x to the minus 2 e to the x, x to the minus 3. I'm going to rewrite those as fractions, putting the powers of x into the denominator. Then I get a common denominator of x cubed, so I have x times e to the x minus 2 e to the x over x cubed. First, I say, when is the derivative 0? Well, to find my critical points. Well, the derivative is 0 when the numerator is 0, which is x e to the x minus 2 e to the x equal to 0. I factor it to get x minus 2 times e to the x is 0. The first factor is 0 when x is 2, and the second factor is never 0. So that's one critical point. 2. The other critical point will be when the derivative doesn't exist. It doesn't exist when the denominator, which is x cubed, is equal to 0. So x cubed equal to 0 happens when x is equal to 0, so that gives us two critical points, 0 and 2. That breaks up our real number line into three subintervals from negative infinity to 0, from 0 to 2, and from 2 to infinity. Okay, so our derivative, again, was x minus 2 times e to the x divided by x cubed. So I'm going to write those factors of the derivative in this table to the left, and here are my three intervals. Now I determine whether each of these factors is positive or negative on each of these intervals. x minus 2 is negative if x is less than 0 and if x is less than 2, but it's positive if x is bigger than 2. E to the x is always positive. 1 over x cubed is negative if x is less than 0, but it's positive if x is bigger than 0. So altogether, for x less than 0, I have negative times negative is positive. For x between 0 and 2, I have negative times positive is negative. For x bigger than 2, I have positive times positive is positive. So the function is increasing between negative infinity and 0, and from 2 to infinity, and it's decreasing from 0 to 2. Next, we'll find the local maximum or minimum. Now, the local maximums and minimums can only occur at critical points. Well, the only critical point where f of x is defined is x equal to 2. X equal to 0, it's not defined. So I use the first derivative test. See how the sign of f prime changes at x, well, or at 2. It changes from negative to positive at 2. So it's decreasing, then it's increasing. That means I have a minimum. So there's a local minimum at 2, and the y value there is e squared over 4 because we're actually going to plot this point, so we care about the y value. Okay, so now let's look for concavity and inflection points. So what I'm going to do here is start with this expression for the first derivative and take the second derivative, which you can check is equal to this expression. Now I'm going to convert all the powers of x into the denominator, and then get a common denominator, which gives me x squared e to the x minus 4x e to the x plus 6 e to the x over x to the 4th. Now to find inflection points, I set this equal to 0. Well, this is equal to 0 when the numerator is 0. X squared e to the x minus 4x e to the x plus 6 e to the x equal to 0. I'll factor out e to the x, and I'll multiply with e to the x times x squared minus 4x plus 6 equal to 0. Now, e to the x is never 0, so if this is 0, then x squared minus 4x plus 6 has to be equal to 0. Now, you could go ahead and try to factor it. You're going to fail. Let me compute the discriminant of this quadratic equation. It's b squared minus 4ac, so negative 4 squared minus 4 times 1 times 6 gives me 16 minus 24, which is negative 8, which is less than 0. So there are no solutions. So actually, this is never equal to 0. There are no inflection points. Now, actually, when we figure out concavity, we should always be concerned also with places where the second derivative doesn't exist, and it doesn't exist at 0. It's possible for the concavity to change from up to down at a place where the derivative doesn't exist. So we're going to check that. To the left of 0 and to the right of 0, see what the concavity is. Well, here are the factors of the second derivative, x squared minus 4x plus 6, e to the x, and x to the 4. And we just showed that x squared minus 4x plus 6 has no solutions. So that means that it's always going to be positive or negative, and since it has a positive leading term, it has to be positive always. So it's positive on both sides. E to the x is always positive, and x to the 4, which is the denominator of our second derivative, is also always positive. So positive times positive divided by positive is positive. Positive times positive divided by positive is positive. This is always going to be concave up. Great. This also furthermore reinforces the fact that we have a local minimum at x equal to 2, because according to the second derivative test, if the second derivative is positive, we have a local minimum. And now we can start filling in the graph. So I have our axes here. Let's see. My asymptotes were x equal to 0 and y equal to 0. I had only one interesting point, which was 2 comma e squared over 4, and that was a local minimum. I didn't have any intercepts. I didn't have any inflection points or anything like that. Okay. Now, as we went to the left, remember that the limit of the function was 0. So that means as we go to the left, it's going to get closer and closer to the horizontal asymptote over here. As we go to 0 from the right, the limit went to infinity. And the function is always increasing on this interval from negative infinity to 0 and always concave up, so it has to look something like this. It approaches 0 as we go to the left. It approaches infinity as we go to 0. It's always concave up and it's always increasing. Okay, now to the right. We know that as we approach 0 from the right-hand side, we go to infinity again because of the limit at 0. And then we know that we reach a minimum at this point. We decrease between 0 and 2. We reach a minimum at 2, and then we're increasing to the right of 2. Furthermore, it's always concave up, so it's going to be sort of U-shaped. And as we go off to the right, y goes to infinity, so the curve is going to continue up and to the right. So it looks something like this. All right, so as we approach 0 from the right, we go up to infinity. It's U-shaped. We reach a minimum at 2, and then it continues off to infinity. So this is our graph of e to the x over x squared. Okay, so here is question 2. Sketch f of x equal to e to the x. Follow all the steps that I suggested in the problem of e to the x over x squared.